Okay, here we are in chapter 6 talking about enzymes, and of course, probably half at least of proteins are enzymes. So that's a lot of proteins, and this is one of the main things that they do is catalyze reactions. So enzymes are the catalysts of nature. Most of these are proteins. There's a few RNA-based enzymes, but they're mostly protein-based. And in a few cases, the protein can be enhanced by special molecules we call prosthetic groups or cofactors, which allow them to catalyze other reactions that the amino acids themselves would not be capable of. As you saw in hemoglobin, of course, there's no amino acid that can bind oxygen very well or at all. So heme would be a prosthetic group for hemoglobin. Now, all catalysts speed up a reaction by lowering the activation energy. And in the case of enzymes, these are catalysts that are very specific in terms of which reactants they bind and which reaction they catalyze. We think of the reaction taking place on the surface of the enzyme, usually in a special place that we call the active site. But of course, the equilibrium is not going to be affected by that because the equilibrium is determined by the free energy of the reactants and products. So delta G, the difference in free energy, that will determine the equilibrium. And all the enzyme does is change the energy of the transition state. That is the highest energy state between the reactants and products. The uncatalyzed reaction, you have a barrier like this. The catalyzed reaction, we have a barrier that's lower, and therefore it's easier to get the reactants to that energy, to that transition state, than it would be for a higher energy transition state. So the transition state is essentially, we define that as the highest energy state. That's going to be an intermediate that the reactants have to go through on the way to becoming products. So there are probably several, of course, intermediate states, but the transition state is the one where the energy is at a maximum. And so that's going to be the highest barrier. The activation energy, delta G double dagger, is the difference in energy between the ground state of the reactants and the transition state, okay, at least for the forward reaction. And the larger this is, the less likely the reactants will be at the transition state, and so therefore the slower the reaction. Enzymes catalyze a reaction by lowering this barrier and therefore making it more likely for the reactants to get to that point. It's also because catalyzed reactions, the transition state usually is not the same transition state as in the uncatalyzed reaction. Therefore, it gives you an automatic mechanism why the energy would be different because it's not the same transition state. And like I said before, the place where the reaction is taking place on the enzyme, we call this the active site. And when the reactants are bound there, we call them substrates. All right, so now we've essentially changed reactants to substrates, and here we're considering the uncatalyzed reaction. That rate is going to be the difference, is going to be related to this barrier here, the difference in energy between the substrate and the transition state. For the forward reaction and for the reverse reaction, it'll be the difference in energy of the products in the transition state. In this case, since substrates going to products is favorable, the reverse rate will be slower than the forward rate, but they'll both be pretty slow. The equilibrium, of course, will be determined by delta G. In this case, delta G not prime, the way they've written it here. I guess if everything's 1 molar, that would be the case. In the case of a catalyzed reaction, we have these other intermediate states. For example, enzyme substrate bound to enzyme. We have an enzyme substrate complex. Substrate going to product on the active site. So now we have an enzyme product complex and then enzyme releasing product. Notice the delta G of the reaction has not changed because we start with free substrates and we start with free products. But now the highest energy state along this enzyme catalyzed trajectory is going to be lower in energy than the highest transition state, or the highest state in the uncatalyzed reaction. And this is going to be the rate that determines, this is going to be the barrier that determines the overall rate. And so therefore we have a higher rate, a faster reaction. The difference in energy between these two transition states we can define as delta GB. This would be related to the difference in rates. But I'm not really going to get into that. Here's a different picture of the same thing. Probably a little more realistic picture because if enzyme binds substrate, the enzyme substrate complex should be lower in energy, right? Otherwise it wouldn't bind. So this is actually a better picture. So you kind of go into a little bit of a barrier, a little bit of a well here. And so you got to go higher up to get to this transition state. But that transition state is still lower in energy than substrate going to a transition state by itself. So this barrier here from enzyme substrate to enzyme transition state is still smaller than going from non-enzyme bound substrate to transition state. That would be this delta G, okay, the non-catalyzed reaction. So we can define a equilibrium constant for the reactant going to transition state. So it's the transition state over the reactants, and then we just basically define this the same way we did delta G's and KEQs. This is now the KEQ, the equilibrium constant for the transition state. This is going to be a very, very small number, okay, a tiny, tiny number, because this is a very unfavorable reaction to go from the ground state of the reactants to the transition state. We can define the rate constant of a reaction as K is KBT, the Boltzmann constant times temperature over the Planck constant. That KBT over H is about 6 times 10 to the 12th per second. But we're going to multiply that by K double dagger, which will be a very, very small number. So we're multiplying a very large number by a very small number, actually a really, really small number. So this rate will be, well, it depends on what this product is. And that's the rate constant for the reaction. We're going to get more into chemical kinetics here for a second. So if you have a simple first order reaction, that's so basically it's first order. The velocity is going to be the rate of increase of product over time, or the negative of the change in reactant over time, because of course that's going to be a negative rate, right? I mean, reactant's going to go down as product goes up. So if we were to draw that out, so if we had change in concentration over time, product would be going up, reactant would be going down. Although it won't look linear like I've drawn it here. It would actually look more like this if it's the first order rate. So product would be going up like this, and let me just pick a different color for reactant. Reactant would be going down like this. So a first order rate depends upon only one concentration. We'll get into second order rates later. So more realistically, of course, we don't just have one rate. We have a forward rate and a reverse rate. So usually K1 and K minus 1. So the velocity of the reaction, the rate, is going to be dP over dt, which is going to be K1 times reactant concentration minus K minus 1 times product concentration. That is the rate of the forward reaction. So dP dt, actually wait a minute. So this rate here is just going to be K1 times reactant concentration. So the rate of reactant going to product, the rate of product going to reactant is just going to be K minus 1 times product concentration. Okay? So the overall change in product is going to be the rate of forming product minus the rate of product going back to reactant. Okay? At equilibrium, those two rates will be equal. So this will be true. The equilibrium concentration of reactant times K1 will be K minus 1 times the equilibrium concentration of product. If we do the ratio of these, we'll get K1 over K minus 1, which, of course, the equilibrium constant of P over equilibrium constant of R is just KEQ. So this is just another way of looking at KEQ. And it's also the same as the ratios of the intrinsic rate constants. We can have second order rates as well. Notice that with this reactant here, it's not automatically going to be K, a rate constant, times A times B. You'd have to determine the order of the kinetics by doing an experiment. It might be K1 times A. It might be K1 times A squared. You really don't know until you do the work to determine the order of the rate. Same here. If it was simple, forward rate would be K1 times A squared. Again, you'd actually have to determine that experimentally.